Right lads, in this video I'm going to go through the question on page 35 for the tetrahedron. It tells us the plan of the base of a tetrahedron is shown in figure 2.37. It's just this picture over here. Edge AB rests on the horizontal plane. So this edge here rests on the horizontal plane, therefore it's going to be a true length. Draw the plan elevation of the solids. So I have the question set up here already, showing AB, and then I'm told that the other point on the base is 60 mil away from corner A. So what I need to do is take 60 mil on my compass and swing an arc. So I've been given no other distance, but I know if edge AB rests on the horizontal plane like this here, and it's a tetrahedron sitting on the ground, all sides are going to be 75 mil, as the length of AB is 75. But because the tetrahedron is tilting upwards, the shape now turns into an isosceles triangle. So the further up I tilt this, these two sides get shorter and shorter. The base stays the same length at all times. I'm told it's going to be 60 mil. So you can see there, just where that point hits there, this length here appears as 60 mil now as well, turning the equilateral triangle into an isosceles triangle. So I can swing 60 there too, turn the equilateral triangle into an isosceles, as the tetrahedron has been raised above the ground, basically hinged off side AB. So that's the plan view I now have. In order for me to actually see what the plan looks like when it's actually tilted up, I'm going to put the tetrahedron on the ground first. So basically, I'm sitting in this sort of position here to put it flat on the ground. So I want to make sure I hinge that right down onto the ground. So if it's sitting flat on the ground, all sides are going to be 75 mil because the tetrahedron is made up of equilateral triangles. So I take my 75 and I swing it there and there. I can connect those together. And as always, when we're drawing the base of our tetrahedron, our plan view looking directly down, we bisect our angles, so all these three here, to find our apex, our top point. So I'm just going to bisect the ones at corners A and B. And where these lines meet, they give me the top of my tetrahedron when it's resting on the ground, not when it's tilted up. So this is flat on the ground now. So what I want to do is take an edge view now to see it. So if I look along the line AB there, I'll see it as a point. That'll give me an edge view of this surface here, and I'll be able to get the height of it then as a result, and that will help me with my elevation later on. So what I do is extend my line AB and my other base point here, and my top as well, and I draw my new XY line up here. We call it X1, Y1. As we know, all sides are 75 mil. There's edge AB. We call that corner C there. We'll just call that T for top. So C is also going to be on the ground here. And find the top point. All sides are always going to be 75 mil. So if I look along this line here, I see AB as a point, and a line drawn perpendicular to that. So remember, line parallel to the XY line is a true length in elevation. I can take that 75, I can swing an arc there, and I just extend this point up here, give me T for the top. Now I can draw in what my tetrahedron looks like as an auxiliary elevation looking in this way. What we're told is tilted upwards. So what I need to do is this point here, we'll call that C1. That's been tilted up from C to C1, so I need to take this up here. It's all been rotated around AB, AB being the hinge points. So what I do is I rotate C around, and C rotates around like that there, and that gives us the new position of C there. Call that C1. That connects back to AB, and now we rotate top, because this is rotating up here. T is obviously going to rotate as well. So I rotate T around there, and I can just do very simply is take that distance from C to T and swing it from C1 to find its new position out here, because that distance there is the exact same as that distance there, and that's our new position for T. That now shows us our tetrahedron when it's rotated upwards. And you can see now C1 goes back to its correct position there, and now we can take T back. T will stay along that line there. The new position of T, take it out, gives us that point there. And we can now connect these together, drawing our tetrahedron. And if we look in here, we can't see AB. If we look down directly on top of it, we can't see AB, it's hidden if we look directly down. So AB now appears at the dashed line there. And now we have our plan view of our tetrahedron. So we can see one side here, we can see the second side here, the third is on the back there, and the fourth is the base. All we have to do now simply is take our points up into our elevation. So AB rests on the ground, we take AB up there, A there, B there. C, which was originally on the ground here, has now been rotated up to that height. So I take the new position of C here, take the height of it, mark it off there. So A, B, C are all now drawn. And the next one we need to take is my height for this point here for T. Take that height there. There's my new position of T. Take that up as well. I can mark that there too. And now you just connect all the points together. So you can see A connects to C, C connects to B, B to T, T to A. That's our elevation drawn there, where the tetrahedron is tilted upwards into position. Just to show colour for some of my points, just take red there. This height here, I got from here. And just some blue for another one. I took my height here. And like that there. So hopefully that video helps anybody who might have been stuck on that question.